Let's see. All right, so what do we measure distance in when we're in the science classroom? Meters. I don't know if you know. Some of you know. What do we measure force in? Newtons. That's the metric system measure of force. If we're in the United States, we measure force in pounds. Okay. A scale actually doesn't tell you your mass. It tells you how much you weigh or your force that the Earth's pulling down on you. So when you get on a scale, it's telling you a force, how many pounds. So if you were to pull something like a chair, like across a floor, you might exert a force, and that force might start off and increase, and then as you get it moving, it might decrease, something like that. And if you wanted to actually find out, let's say like the area under the force curve, you could use the definite integral, right? You could find the definite integral from a to b of f of x dx. And in this case, what are the units for the definite integral? No per, because Newton meters or meters, newtons. When we do the definite integral and we find the area, we're doing length times width, right? It's not like the derivative where we're doing like the rate of change. So the units would be Newton meters, and actually physics friends might know that as something else. It's work. Work is force times distance, and we measure work in joules. Oh, physics friends. All right. If you're in physics, you should know that. If you're not, you're not responsible for knowing it, but it is an interesting thing to see. In physics, we have a relationship that work is equal to force times distance, and if we do it based on calculus instead of algebra, here it is. This area is force times distance, but for lots of little rectangles, it's force times distance. So we can use the integral, and when we want to do it for using calculus, work is the integral of the force function. Whoopsie daisy. And you can see that newtons times meters is joules. As a matter of fact, we can do that really with most any graph. If this is velocity in meters per second, and that's time in seconds, the units for the definite integral? Nope. Meters, right? Why? Because the definite integral is going to be meters per second times seconds. Just like the definite integral here was newtons times meters. If we have points per game and games, points. All right. If we have monkeys and bananas, you get banana monkeys. Now it's a ridiculous unit, right? No. Of course not. But the important thing is that it's not bananas per monkey. That's what it would have been first semester when we were talking about rates of change. When we're talking about definite integral, we're talking about the product of those two. I think, let's see, I think you're actually, let's see, kilowatts and hours. I think this is how the power company charges you. If you measure how many kilowatts of energy you have over time, can you imagine it doing something like that over a long time? Maybe you use a lot of energy during the day and not so much at night. What's the area here measuring? Kilowatt hours. All right, and let's see. Well, I'll leave that. Yeah, I was gonna, what was I gonna do? Okay, so, because you're in physics, if you're not, it's okay. A watt is the measure of energy per second. A watt is a joule per second, and hours is a measure of time. So it's like, 3,600 seconds or something like that. So if you want to know what kilowatt hours is, the seconds go and you get joules times 3,600, you get energy, right? So the power company sells you power, like watts per second, over an amount of time, and what they're actually selling you is energy. Okay? All right, so everyone else can tune back in. We're done with physics for a little bit. Is that okay? Yeah. So the first, 7 or 8 problems that you're going to look at tonight is really just going to ask you, hey, what would the units of this be? And I guess what I'm trying to say is I think the first, 7 problems are going to take you 2 or 3 minutes, would be my guess. If it doesn't, you can come back and tell me, hey, you were really wrong. And that's fine. What I want to focus on today is really the fact that first semester we took a look at, let's see, I will do, all right, so if we took a look at the velocity function, nope, sorry, let me try that again. If I took a look at the position function, right? First semester we looked at position and we talked about the rate of change at a specific point, which would be the velocity, right? And I think if we had to draw the velocity function for this, how would you describe what the velocity of this function might look like? Linear? Does that seem okay? If the function looks like it might be quadratic, the derivative might be linear. And what would the units for the derivative be? Meters per second. And this would be the velocity, right? Okay. So first semester we started with position and talked about velocity. This semester we started with velocity and talked about position. We actually said, hey, if you look at the area here, that's how far you went, right? Okay. So there really is a very clear connection between the derivative and the definite integral. As a matter of fact, they're inverse operations. Okay? The first semester we did division, we did a rate of change, and we went this way. The second semester we're doing an area, which is a product, and we're going this way. All right? That's a piece of what it is that we're doing. We're not there yet to call it that. We're not there yet to really learn the rules. But yeah, eventually, David, we're going to be doing the derivatives backwards. So if you could go from position to velocity, there's this notion that you can go from velocity to position. Okay? And you've already been sort of doing this. And this is what the fundamental theorem of calculus says. The fundamental theorem of calculus, I'm going to write it once. I'm going to say it. We're going to look at a couple problems. I'll write it again. I'll say it again. And I'll probably try writing it a couple different ways because different books use different things. But the fundamental theorem of calculus says if you were to take the definite integral of the derivative it gives you the change in the function. So another way of looking at it is this definite integral sign and this derivative sign, they undo each other. So the definite integral from a to b of a derivative, the definite integral and the derivative undo each other so that the only thing you have to worry about is f of b minus f of a, just the difference in the functional values. All right, so one way of thinking about it is the definite integral and the derivative undo each other. Another way of saying it is that the definite integral of a derivative function is the change in functional values. we are going to do an example, and then we're going to go back to what I just said and see if we can actually understand what that means. Okay? So, I'm going to take a function like x squared. Is that okay? All right. The derivative of x squared? Hey, you guys are good at that. All right, so the derivative is 2x. So my claim is that if we take the definite integral of the derivative, it will tell us how much the function changed. So let's do this. Let's take from 0 to 1 of 2x dx. Now, we obviously don't know a rule for the definite integral. It is. That's awesome. Okay? And we are going to try to take a look at some. So, David says, that's a triangle. All right, so talk to me. It's a triangle. All right, David said the area is 1/2 base times height. The base is 1. The height is 2. How'd you get 2? When you plug 1 into 2x. So that definite integral is 1. Is that okay? I would like to make a connection. I have a point here, 0, 0, and I have a point here, 1, 1. We haven't established a pattern yet, but we're going to start to see it, I hope. All right, definite integral from 0 to 2. I think the definite integral from 0 to 2 is just a bigger triangle. Let's see. The base now is 2. The height, what do we get, 4? Okay. I would like to make a connection here that there's a point on this graph that is 2, 4. So the derivative from 0 to 2 is 4. And the function went from 0, 0 to 2, 4. Not only that, let's just take an intermediate step. What if I found the definite integral from 1 to 2? Whoops. Sorry.
No, it's not a triangle anymore.
Ian's not going to do any work, and he's going to say 3. Can you tell me why? You're right.
The integral of 0 to 2, and then the integral of 0 to 1.
Ian's saying, look, if we already found the area of the big triangle, and we already found the area of this little triangle, what's left must be the difference, so it's 3. Hey, there's a point here, 1, 1, and 2, 4. When x goes from 1 to 2, what's the change in the y value? 3, right? Do you see that Ian did 4 minus 1 to get the area to being 3? And here we can do 4 minus 1 to get the functional value difference is 3. Let's do one more, and then we'll go back to what I originally said. So from 0 to 3, that's a lot of area. The base is 3. The height is 6. The area is 9. Hey, guess what? There's a point on this graph, 3, 9. Yeah, it does. As a matter of fact, that's what the fundamental theorem calculus tells us. So I want you to think about this. First semester, if we looked at the derivative and we saw that the derivative was positive, do you agree from 0 to 3 the derivative is positive? What would that tell you about the function? It's increasing. Here's what I want to tell you. Not only do we know the function's increasing, but now you can tell us exactly how much it's increasing. So before, all you were able to say is, oh, on 0 to 3, the function's increasing because the derivative's positive. Now you can say, on 0 to 3, the function's increasing 9 units, because that's how much area is underneath the derivative function. So the area, or the definite integral, of the derivative is exactly how much the function changed. So I'm going to go back to what I wrote up here, and I'm going to say it again. The definite integral of the derivative function is exactly the change in the functional values. It's how much the function changes. So not only are you going to be able to tell me, oh, the function increases or decreases, you can now say exactly how much it increases or decreases. And that's because of the fundamental theorem of calculus. And I hope I'm not doing a proof of it, right? I'm not proving it to you. You may get a proof of it maybe next year if you do a calculus course in college. Certainly if you go and take 3 semesters of calculus and then you go back and take an analysis course, a real analysis course is where you go back and you prove everything you did in calculus. You would definitely prove it then. But I hope that it's a convincing argument that if first semester we did division and we did rates of change, and now we're doing multiplication and accumulation, they're inverses of each other. Just like position, the rate of change of position gives us velocity, and the definite integral of velocity gives us position. Those are inverses of each other, and that's exactly what we're saying right here, is that the definite integral of a derivative is the rate of change, is the difference in the function. I'd like to do another one, but now's a good time to ask a question. It's going to take a little time for it to sink in. Sam? Dan?
It works for non-quadratic functions too.
It does. The thing about this is right now, quadratic functions have linear derivatives, and I don't need any fancy rules. David can just say, oh, it's a triangle, or someone can say, oh, that looks like a trapezoid. So I can do it, and we can do it using geometry to show that it works. If we do something more complicated, you don't know the rules yet. But you will. Anything else? All right. I am going to write this same rule in a more complicated way, and then we're going to do another example. Let's see. Copy. Paste. Okay, so some books write this same rule like this. They say, let so this is a different rule. Let little f of x be the derivative of capital F of x. Then, here's the rule. So, here's the thing. Dan and David are both right. David says it's confusing, and it is. I'll tell you why. It's confusing because we're using a lowercase and a capital letter F. It's confusing because we're doing this substitution. We're saying let little f of x equal capital, the derivative of capital F of x, instead of just saying, if we just plug this in, we would get this. We would get the derivative, the definite integral of the derivative of capital F is equal to f of b minus f of a, capital F of b minus capital F of a. This is exactly what we said up here, just using capital F's instead of lowercase f's, right? It is more confusing saying it this way. Many books say it that way. And it is the exact same thing as what we said. This actually says that the definite integral of a derivative. Now, it doesn't look like little f of x is a derivative, until you go back and read that little f of x is a derivative. So the definite integral of a derivative is the change in the functional values. So it's another way of saying the same thing, and many, many books say it, and many, many of the problems that you're going to look at are going to be sort of in that. They might say it this way, they might say it this way, and a lot of what we're going to have to do over the next few days is look at how many ways can you ask the same question, and your problem is not going to be answering the question, it's going to be figuring out what they're asking, right? That's what I'm looking for. Okay. Let's take a look at another function. And this is the function y equals x squared minus 2x plus 2. What's the derivative for that function? Man, you guys are good at that. 2x minus 2, so I think it's going to look something like this. Is that okay? And tell me, why does this derivative and this function, like, why do they sort of work together well? It is.
Because the minimum is for derivative class.
Alright, so the derivative is 0 when the function has a minimum. And from 0 to 1, what would you say about the derivative? Negative, which means the function is decreased. From 1 on, the derivative is, which means the function is increasing. So that's how we would have said it first semester. What I want to convince you is, not only that, you can tell me exactly how much the function is increasing or decreasing. Not just say, oh, it's decreasing there or increasing, but we can tell how much. So let's actually look. From 0 to 1, we know that the derivative is negative, and if we find the definite integral of the derivative, I would say that's actually still a triangle with a width of and a height of. Alright, so you can either say a height of 2 and remember that it's below the x-axis, or you can actually say the height is negative 2 because it's below. So, what's that? An area of negative 1? Is that true? So, from 0 to 1, the function not only decreases, it decreases 1 unit. I don't think so. Is it? Did I do it wrong?
Oh,
no, did I do it wrong?
No, you're right.
Are you sure? Because now I'm freaking out a little bit. Okay, good. Okay, so let's see. No, now I'm feeling like I did this wrong.
One half base times A.
did, right?
Base times A is 2. One half of that.
Yeah, that's right.
Is that
Hold on, now I'm worried that, oh gosh, sorry. I'm going to wait, because I'm worried that I messed something up. Yeah, is my graph totally wrong? I think it is too.
It looks wrong.
I think it looks wong too.
Hold on, the function derivative is 2x minus 2, right?
Yes.
Well, if you plug in, oh right, if you plug in 1 and 2.
Yeah, I'm with you, Arnie. Let's see.
What's the function? That's right. That's cool.
Are you sure? X squared minus 2x plus 2?
No, you don't.
Wait, but aren't you? No, it's not right. It's supposed to be n.
Oh, no, it's not right. My function is, alright, so alright, sorry.
The derivative.
The derivative's right. The function's like, it should look like this, right? That's what the function looks like. But yeah, no, it does. I mean, look, sorry. You don't have to just appease me. Like, here's what the function looks like. I had the function going down and hitting the x-axis, which it doesn't do. Alright. Phew! Sorry about that. Okay, so, I know that I have a point here, 0, comma.
1.
Try again.
2.
Right? and here I'll put in my other x mark if you want, 0, comma 2. If you plug 0 into the function, you get 2 out. Here I have a point 1, comma... You have to plug it into the function, folks. Okay, I'm just letting you know. I could go into an Algebra 2 class and say, here's the function, 1, comma something.
1 minus 1. 1. Just kidding. Oh, it's 1.
1, comma 1. So,
Yeah, you're right.
this should... The 1, comma 1 part was the easy. Like you should have... This should confirm, though, that, look, the function is decreasing. Not only is it decreasing, but it's decreasing exactly 1 unit. Why? Because that's how much area is, that's how much area there is under, or in this case, above the
Function. Derivative.
derivative. Thanks, that's the word I was looking for. If we were to continue, right, if we were to find,
Technically, would that be above the derivative?
yeah, that's what I said. Like, it's the area under or above in this case, and because it's above, that's why it gets the negative. We could do one of two things. We could actually go from 0 to 2, or we can go from 1 to 2. If we go from 0 to 2, we see that... What happens here?
Oh, there's a 0 for definite interval, which means that the function comes back to where it was originally.
Okay, so from 0 to 2, the function didn't change at all. As a matter of fact, from 0 to 2, the function comes back to 2, comma 2. The function value didn't change. The functional value stayed at 2. All right? Give me one more second, then we can do a few questions. Alternately, if you wanted, you could say, okay, what did the function do from 1 to 2? Ian, without doing any math or much thought at all, what did the function, what did the definite, what would... Thanks. So you gave the right answer, even though my question was totally botched. The definite integral from 1 to 2 is 1, which means that from 1 to 2, the function increased 1 unit. That's exactly what it did. All right. What do you want to say? Questions, comments? Go ahead.
If you take the integral backwards, does it still work on backwards?
Okay, so if we take the definite integral from 2 to 1 of 2x minus 2, because we're going backward, you get an answer of not 1, but negative 1. And that means when x goes from 2 to 1, it drops 1 unit. So if we're going left to right, the function decreases 1 unit. If we do right to left, it increases 1 unit. So it does still hold. All right, so look. This is the fundamental theorem of calculus. There's another corollary which actually says instead of the definite integral of the derivative, it says the derivative of the definite integral. We're going to do that in a few days. But the main message for today is that the definite integral and the derivative undo each other. They're inverse operations, okay? And there are lots of ways of saying that, and some of them are a little more straightforward, some of them are a little more complicated, but they all say basically the same thing. Go ahead.
You know what I was thinking? What if it's just a coincidence that the slope, well, like the slope between 0.11 and 22 is 1?
I don't know. I have to think about it.
Yeah.
So if
But
you have...
is there a coincidence?